Okay, so let's talk about how to draw Lewis structures. So we learned this back in honors. There's just a couple of additional rules that we add that make it just a little bit more complicated, but I have confidence in your ability to get it. Okay, so the first thing that you need to do when you have a molecule to draw is to figure out the correct skeletal structure. So you know that hydrogen is always terminal, which means that hydrogen is never going to be in the middle because it can only make one bond, so it can't be in the middle. And you generally place the most electronegative elements in the terminal positions and the least electronegative one in the center. And this is not always true, but it's a good place to start. Which brings me to the third point, which is that officially what we want to do is minimize formal charge. And we haven't learned formal charge yet. I'm going to get to it just a little bit later in this video. So for now, we're just going to put that one on hold. After you've figured out the skeletal structure, you're going to calculate the total number of valence electrons. And then if you have a negative charge, you're going to have to add an extra electron for that. And if you have a positive charge, you'll have to subtract electrons for that. So the valence electrons would just give you a neutral atom, but if you have a polyatomic ion, you're going to have to either add or subtract to take care of that. The next thing you're going to do is distribute the electrons to create the maximum number of duets and octets. And then you have to form double and triple bonds if necessary if you run out of valence electrons and you still haven't completed all of your octets. So let's just do a couple of examples of these. Hopefully it will help jog your memory. So you should be able to look at your periodic table and see that nitrogen has 5 valence electrons and hydrogen has 1, and we have 3 of those. So that's a total of 8 valence electrons for NH3. I told you that hydrogen has to be terminal, so that means that nitrogen is going to go in the middle, which I'm going to put here. So nitrogen is going to go in the middle, and we'll put hydrogens the whole way around. Okay, and now we have 8 valence electrons, so we can put 2 here, 2 here, 2 here. That is 6. We've now filled the duets for all of the hydrogens, and we have 2 electrons left, so we'll put them here outside the nitrogen to complete the nitrogen octet. Okay, so that is the structure for ammonia. All right, so for CO2, carbon dioxide, we have a carbon, which has 4 valence electrons, and we have an oxygen. An oxygen has 6, but we have 2 of those, so that's 12 plus 4 is 16 electrons. Okay, so we want to put carbon in the middle because it's less electronegative than oxygen, so we'll put carbon in the middle, and we'll put oxygens on either side of it. Okay, and now we have those 16 valence electrons to distribute, so we have 4 for the bonds, and then 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we've filled the octets for both of the oxygens, but we have not filled the octet for carbon, but we're out of electrons. So this gets to step 4. We want to form double bonds in order to give octets to both. So if each of the oxygen atoms shares more with the carbon than it already is, then that will take these electrons and move them in. So it gives us a double bond, and these electrons and move them in to give us a double bond. And so your final Lewis structure would be the oxygen double bonded to a carbon, to an oxygen, and then 4 non-bonding electrons on each oxygen. So if you add all those up, that's 8 per atom, which is what we want. All right, NH4 plus. This is very similar to the NH3 that we just did. We have 1 nitrogen, which is 5 electrons, 5 valence electrons, and 4 hydrogens, which is going to be 4 additional. So that's 9 electrons altogether, but this has a positive charge. So for a positive charge, that means we have fewer electrons, so we need to subtract 1 from the number we just found, so 9 minus 1 is 8. All right, nitrogen again is going to go in the middle because hydrogen can't go in the middle, and we'll put the 4 hydrogens around it. All right, and then we have 8 valence electrons, so 2, 4, 6, 8 is all of our electrons. The hydrogens all have a duet. Nitrogen has a full octet, and everything looks good. So one thing to note, we covered this in honors, but just to remind you, you need to put the brackets and the charge to indicate that this is an ion and not a neutral molecule. All right, NO3 minus. So nitrogen, again, has 5 valence electrons. Oxygen has 6. There are 3 of them. That's 18. 18 plus 5 is 23. But we have a negative charge, and so that is going to add 1 more. So we have 24 total valence electrons. In this case, again, nitrogen is less electronegative than oxygen, so we're going to start at least by putting that there. And then we have our 3 oxygens around it. Right, so we have 24 electrons to get rid of, so 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24, okay? And now we're out of electrons, but the nitrogen doesn't have a full octet. So one of these oxygens is going to have to make a double bond with the nitrogen. So for right now, we'll just call it this one. So we'll move those electrons in and make a double bond. But it could have been any of the others as well. And so this brings me to my next topic, which is resonance structures. So a resonance structure is a structure that we use when you have multiple structures for a Lewis structure that give the same general outcome. And the actual structure is called a resonance hybrid. So it's really an average of all of the different resonance structures. So let's go ahead and draw the resonance structures for NO3 minus, and we'll talk about what the resonance hybrid would look like. So on the previous slide, I had the oxygen double bonded here, and we had non-bonding pairs the whole way around. All right. But it could easily, oops, I have one extra. All right, but it could also just as easily have been this oxygen over here that had the double bond. Dots there, okay. Or it could have been the oxygen up on top that had the double bond. All right, any of these would be acceptable ways to draw the Lewis structure for NO3 minus ion. And to show that all of these are equally valid, we draw these little double-headed arrows between each of them. And again, we want to put it in brackets and do the minus. And so what this means is that actually none of these is the correct structure. The correct structure is actually an average of the 3. So if we were to draw the resonance hybrid, we would have the nitrogen with 3 oxygens coming off, and each of them would have 1 and a third bonds to the nitrogen. Okay, so this is not a very descriptive way because it's, or not a very clear way to draw it because it's difficult to assign where the non-bonding electrons would be and things like that. But this is actually experimentally what we find out the NO3 minus ion looks like. So all of the nitrogen-oxygen bond lengths are the same. They have the same strength. So it's not that just one of the oxygens has a double bond and the other ones are all single. You actually get 1 and a third bonds for all of them. So now let's talk about the concept of formal charge. So a formal charge is a fictitious charge that's assigned to each atom in a Lewis structure and helps us determine which structure is going to be the most stable for different Lewis structure options. Okay, so this is not an actual charge associated with the atom. It's a construct that we've made to help determine what makes the atom most stable. So you get the formal charge by doing the number of valence electrons minus the unshared electrons minus half of the bonding electrons. So this is basically an assessment of the difference between how many electrons that atom brought in to the compound as valence electrons and how many it's sort of taking responsibility for in the compound. So we're going to do a couple examples just to make this a little bit more clear. So a couple of rules about formal charges. First, the sum of all the formal charges in the compound has to be 0 if it's a neutral compound. The second is that the sum of the formal charges in an ion has to equal the charge of the ion. So if you have an ion with a -2 charge, when you add up all the formal charges, you should get -2. If the third is that molecules with the smallest and least number of formal charges are more stable or lower in energy. So we want to minimize the formal charges in our structures. And the fourth is that if formal charges can't be avoided for a molecule, then the negative charges should go on the most electronegative elements. Okay, so let's use formal charges to determine which of the following structures of carbonyl sulfide is the most stable or the lowest energy. All right, so let's start with oxygen. Oxygen has 6 valence electrons, and here it's got 6 non-bonding electrons and 1 bond. So that's going to count as 1 electron, even though there's 2 electrons in the bond. So this is going to be 6 minus 7. So the oxygen here is going to have a formal charge of -1. All right, carbon comes in with 4 valence electrons, and it's forming 4 bonds. So we're going to count each of those bonds as 1 electron, which would be half of our bonding electrons. So 4 minus 4 is 0. Okay, and then for sulfur, sulfur also has 6 valence electrons, like oxygen does. It has 2 non-bonding ones here, so that would be -2, and then it's forming 3 bonds, so that would subtract 3 more from that. So 6 minus 2 minus 3 is going to give us a +1. Okay, so we have satisfied the requirement that all of our formal charges add up to be 0, because +1 plus -1 is going to give us 0. But we do have formal charges here, so this might not be the most stable structure. Right, so let's take a look at B. So oxygen here again has 6 valence electrons to start. We have 2 non-bonding pairs and a double bond. So that's going to be 2 electrons from the double bond and then 4 from the non-bonding. So that'll be 6 minus 6 is 0. All right, carbon comes in with 4 valence electrons. It's forming 4 bonds, which is going to count 1 electron for each bond. So 4 minus 4 is 0. And then sulfur comes in with 6 electrons. It has 4 non-bonding electrons, or 4 unshared, and it's forming 2 bonds. So we're going to count 2 electrons for each of those. So 6 minus 4 minus 2 is going to be 0. Okay, again, all of our formal charges add up to 0, so that's good. And then for the last one, the oxygen here has 2 non-bonding electrons and makes 3 bonds. So we'll have 6, which is the valence electrons, minus 2 for the unshared, minus 3 for 1 in each bond, gives us a +1. And then carbon again comes in with 4, makes 4 bonds, so again it's going to be 0. And sulfur comes in with 6 valence electrons in this structure. It has 6 non-bonding electrons and 1 bond, so that's going to give us a formal charge of -1. Okay, so in all of these cases, these are all structures that are valid, but the most stable of them is the one that has all 0 formal charges, and so that would be B in this case. Now I'm going to talk about a couple of exceptions to the octet rule. The first of these is free radicals. So given that all of our bonds have 2 electrons, and we often look at non-bonding pairs, and if something's going to have 8 electrons, it has to have an even number. So free radicals cause a problem for this because a free radical is a molecule or an ion that has an odd number of electrons. Okay, they're also sometimes just called radicals. So one example of this is NO. So nitrogen has 5 valence electrons and oxygen has 6. So altogether that gives us 11. So if we want to draw the structure of nitrogen monoxide, there's nothing to go in the middle because we just have a nitrogen and an oxygen. Okay, we have 11 valence electrons, like I said. So we're going to start with 1 in the middle, and then, so that's 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, okay? So here oxygen has a full octet, but nitrogen only has 5 electrons, so we're going to take off 2 from the oxygen and make a double bond there. All right, so oxygen still has 8, and now nitrogen has 7, which is about as good as we can do for this particular example because we can't give nitrogen 8, and it can't hold 9 because that would be more than a full octet. Okay, and we could use formal charges to determine that nitrogen is the one that should have the odd electron because it came in with 5. So if we count our 3 non-bonding electrons and 2 from our bonds, 5 minus 5 is a formal charge of 0. And same thing for oxygen. If we count our 4 non-bonding plus 2 from each, or 1 from each of our bonds, 6 minus 6 would be a 0 formal charge for oxygen as well. So this is the most stable structure for nitrogen monoxide, which is a free radical. All right, the next exception is an incomplete octet. So there are some examples where you can't fill the full octet just because there aren't enough electrons there to do that. And the most common example of this is boron. So here, boron has 3 valence electrons, and hydrogen, each hydrogen has 1 electron, so 3 plus 3 gives us 6 altogether. So we're going to put boron in the middle because hydrogen should be terminal. We'll put a hydrogen around each edge there. We have 6 electrons, 2, 4, 6, and now we're out of electrons. So we don't even have enough electrons to give boron 8 electrons, and that's okay. So this is one exception where it's fine that you only have 6 electrons. The final exception that I'm going to talk about today is expanded octets. And an expanded octet is just what it sounds like. It's when the central atom actually has more than 8 electrons. And this can't happen for every atom on the periodic table. The element has to be in the 3rd row or below. And this is because once you get to the 3rd row of the periodic table, you now have d orbitals available, and so there's room for more electrons to be added. So when you're in the 2nd row, once you fill up the p orbitals, that's all that you have left, and so you can't add any more than 8. So here we have SF6, and sulfur, as I've said a few times, has 6 valence electrons, and fluorine, being in the next to the last column there, it has 7 valence electrons. So 6 times 7 gives us 42 electrons from fluorine, and then 6 more from sulfur, which gives us 48 altogether. Okay, so let's start by putting sulfur in the middle because it's much less electronegative than fluorine, and we'll put the 6 fluorines around the sulfur. 4, 5, 6 of them. Okay, and then the first thing we're going to do is draw bonds. So we have 2, 4, 6, 8, 10, 12 electrons there. And now we'll start filling in the octets of the fluorines. So that's 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36, 38, 40, 42, 44, 46, 48. Okay, so now I've used up all of the valence electrons. All of the fluorines have a full octet, and the sulfur actually has more than an octet. It has 12 valence electrons, but that's okay because it's in the 3rd row, so some of that overflow is going to go into the d orbitals. And you don't really need to know where it goes, you just have to know that in the 3rd row and below that's a possibility. All right, now let's do BRF3. So bromine has 7 valence electrons, and fluorine also has 7. So altogether, that's going to give us 28 valence electrons. Fluorine is more negative, more electronegative than bromine, so we'll put bromine in the middle. Okay, and we'll put the 3 fluorines around it. Okay, and then we have 2, 4, 6 electrons for the bonds, 8, 10, 12, 14, 16, 18, 20, 22, 24, and I said there were 28 electrons, so there's no more room around the fluorines because they're in the 2nd level, and so they have 8, and that's as many as they can have. So the remaining 4 are actually going to go on the bromine atom, okay? And so in this case, bromine, again, has more than 8 electrons. So it's got 3 bonds, which is 6 electrons, and then 2 non-bonding pairs, which is a total of 10 electrons. Okay, Xenon Tetrafluoride is down here. So xenon is a noble gas, and I understand we've so far not used noble gases in any bonding, but the ones down farther on the periodic table do sometimes make bonds, and xenon is one of them. So xenon is Xe, and it has 8 valence electrons, and fluorine, there are 4 of them, each one has 7, so 8 plus 28 gives us 36 electrons altogether. So we'll put our 4 fluorines around. All right, and then that gives us 8 electrons in bonds. 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. All right, and we had 28 plus 8, we had 36 total electrons here. And so that gives us 4 more that we need to figure out where to go, and they're also going to go on the xenon because the fluorine can't take them. Okay, so again, another example of an expanded octet. And maybe you're thinking, how would these look in 3 dimensions? We didn't talk about anything that had more than 4 electron groups in honors, and we'll get to that in the next lesson. All right, and then the last example I have here is POCl3. Okay, so phosphorus is in the 3rd row. It has 5 valence electrons. Oxygen is in the 2nd row. It has 6 valence electrons, and chlorine, each one of those is going to have 7. So we're going to have 5 plus 6 is 11, plus 21 is 32 electrons. Okay. In this case, the most likely element to go in the middle is going to be phosphorus. It's the least electronegative, so we're going to stick that in the center here. Okay, and then we'll put the oxygen and the 3 chlorines around it. Okay, and now we've got to start distributing those electrons. So we have 2, 4, 6, 8. And now we'll add 10, 12, 14, 16, 18, 20, 22, 24, 26, 28, 30, 32. All right, so it looks like everybody's happy. We've got a full octet for everyone. But in this case, this is one where you really need to calculate the formal charge to know that you have the right structure. And I didn't do that in the other 3 examples just for the sake of time in the video. But if you go back and calculate the formal charge on all of the atoms in the 3 structures we've already done are all 0. In this structure, they're not. So if we think about how many valence electrons chlorine has, it comes in with 7, and then it's got, each of them has 6 non-bonding ones and then 1 bond. So that's 0 for all the chlorines. The phosphorus came in with 5 valence electrons, and it's making 4 bonds. Okay, so that gives it a formal charge of +1. And the oxygen has a, it came in with 6 valence electrons, and it has 6 non-bonding electrons and then 1 bond, which gives it a formal charge of -1. So we haven't reached our most stable structure because our formal charges aren't all 0. And so the way to get the formal charges to be 0 is to have the oxygen have 1 less electron and the phosphorus have 1 more in our counting scheme. And so what that means is that we need to make a double bond. So we'll take away 2 of the non-bonding electrons and now have a double bond. And so now the oxygen came in with 6 valence electrons. You subtract the 4 non-bonding and then 2 for the 2 bonds it makes, which gives 0. And phosphorus had 5 valence electrons when it came in and is forming 5 bonds, which subtracts 5, which gives it a formal charge of 0. So this is another case where we are not following the octet rule strictly, and that's because phosphorus has that ability to take on more electrons to give itself a 0 formal charge. Okay, so this wraps up our drawing of Lewis structures. We're going to do a lot of practice with this and eventually predict 3D structures from these, but this is all we're doing for drawing Lewis structures.